Hello, we start with a new lecture, Kinetics and Stability. I am sure all of you have heard about expiry date and shelf life and best before date and things like that. We relate today's lecture with those concepts, and we have to have an understanding of the reactions and mechanisms that are involved with the concept of stability. If we define kinetics, it's concerned with the reaction rate and sequence of steps by which reaction occurs. So kinetics deals with rate or speed of reactions and the steps of the reaction or the mechanism of the reactions. What about rate? What does rate of reaction mean? It's the speed with which the reactant disappears and the product will form. And this sequence by which the reaction happens is called mechanism of the reaction. Why do we study kinetics? Because it gives us an idea about the mechanism of the reactions that have been happening with our product or drug or like chemical entity or substance. And it gives us a way to predict the degree of change that will occur after a given time. This means the study of kinetics gives us the ability to have an expiry date or to know when will the drug or the product will change to a certain extent that we will decide on. So why do we study drug stability? Because it's important for the final consumer of the product. We have the obligation to give safe products to the patients. So a stable drug means a safe drug. We don't want to give a drug that has a low effect to the patient, or the drug has been degraded or has changed to other chemicals or to toxic products. Now, if we define drug stability, it's the resistance of the drug in the various chemical, physical, and microbiological reactions that may change the original properties of the preparation during transport, storage, and use. This is a pharmaceutical definition for drug stability. So we have to monitor chemical, physical, and microbiological changes to the product. And quantitatively, it is being expressed as shelf life. You will hear this term more frequently in the future. Shelf life is the time during which the medicinal product is predicted to remain fit for its intended use and the specific conditions of storage. So shelf life is, in pharmaceutical settings, it means the duration at which the product remains fit for its intended use. So we have to decide on this. What is intended use? We have to decide on this. It's not like shelf life means the drug has disappeared or completely degraded or it has changed to something else. We will decide what is shelf life based on some parameters that we have to define and at specific conditions of storage. Or it's the time from manufacturer or preparation until original potency or content of the active ingredient has been reduced by 10%, which is the limit of chemical degradation. So here is the intended thing that we talked about. Generally, as a general rule, in pharmaceutical applications, we we call shelf life, the time by which 10% of the effect of the drug has been reduced. We have a new term, half-life. What do you mean by half-life? It's the time required for 1/2 of the material to disappear, or the time at which concentration will decrease to half of the original concentration. And this diagram shows us a depiction of this thing. This is the amount, and this is the time by which the concentration has decreased to the half of the original concentration. Stability is affected by many factors: temperature, humidity, light. Here we have to know what are the mechanisms of reactions that will affect or that are involved with the decomposition or degradation of pharmaceutical products. Now, we know that kinetics deals with stability of pharmaceutical products, and we know it's important to predict stability of pharmaceuticals. Well, it's also important to know the factors that affect stability, and as we said, these are examples of factors that affect it, and this is an example that shows how environmental factors can affect stability. Because I don't want the video to be too long, I have to rush through slides. Rate of reaction. We said that this means the speed or velocity of the reaction, or the speed at which the reactant will react and the product will form. And we have this rule that all of you have to know, because you have studied this before. Here K is the constant, and this is the concentration of the reactants, and this exponent is the number of reactants that have reacted, and this is the rate of the reaction, because rate equals change in concentration of the reactant over change in time. Now, when we have more than one reactant, this exponent will be higher. Now you know what is rate, and you have studied that. What about reaction mechanism? Reaction mechanism means the steps of the reaction. Each reaction can be composed, or it can be composed of smaller reactions that the overall reaction will give us the final formula that we have. One of the slowest step in a multi-step reaction is called the rate determining step. And we have talked about this in detail. I think it was in the first semester, so we will not spend so much time with it. Rate of reaction is the speed or velocity of the reaction with which a reactant or reactants undergo change, or it's the rate at which the product will form or reactants will disappear. This is a general rule that all of you have studied before. Rate equals change in concentration of reactant over change in time, and we can have a constant, and this is the concentration of reactant, and this exponent refers to the number of reactants. If we have one reactant, A will be 1. If we have 2, it will be 2, and like that. This is a general rule that I'm sure all of you have heard about. Now, we know what is rate of reaction. Let's talk about mechanism of reaction. By mechanism, we mean steps. Let's see, we have a reaction. A plus B plus C equals ABC. This is called overall reaction. This can be composed of two elementary reactions. Let's say A plus B equals AB, and then AB plus C equals ABC. These two are called elementary reactions, and this is called overall reaction. That is what we mean by reaction mechanism. The reactions can happen in number of steps, and usually one of these steps is the slowest one, which like governs the speed of the overall reaction. Or we can say that speed of the overall reaction depends on the speed of the slowest step of the elementary reactions. So this slowest elementary reaction is called a rate determining step. We have talked about this before in the first semester in detail, so we will not go into so much detail. An example of an overall reaction and its elementary reactions. Now let's talk about order of reactions. We start with zero order reactions. Zero order reactions are those in which the rate of the reaction does not depend on the concentration of the reacting species. So the rate of the reaction will remain constant, as you see here. With time, the rate is constant. In zero order reactions, with time, the concentration of the reactants will decrease, and this relationship is a straight line. So change in concentration of the reactant is constant with time. We call these zero order reactions. Sorry. We know what is half-life. To find out the half-life of zero order reactions, we have this formula. You can find out how we got this formula, but because we don't have that much time here, if you had any questions, you can ask later. First order reactions. In these reactions, the rate of the reaction depends on the concentration of the reacting species. As you see in this diagram, we have time and we have concentration of the reactants. With time, the concentration of the reactants will decrease, but as you see, we have a curve here, which means the rate has decreased with time. So these are first order reactions, and this is another example. We can take, for example, this block here, and you see what a change in the concentration has happened. But if we take this block here, the change is much less. The rate of the reaction is much less because the concentration of the reactant has decreased. But the relationship between time and logarithm of the concentration of the reactants is a straight line with first order reactions. And for half-life of these reactions, we have this formula. As you can see in the half-life formula, we don't have anything related to the concentration of the reactants, because half-life in first order reactions is constant, but half-life in zero order reactions changes with concentration. So it's exactly the opposite of the rate. Rate with first order is, it changes, but half-life does not change with time. But in zero order reactions, rate does not change, but half-life changes with the concentration of the remaining reactants. We call something called apparent zero order reactions, which happens only in suspensions, in which we have particles like this, like this, in a media or in a medium. Why we call these apparent zero order reactions? because the reaction of solubilization of these particles or degradation of these particles is a first order reaction. Sorry, not the particles. These particles are like suspended in the medium. So some of these particles will dissolve in the medium, and the dissolved component will degrade with time. The degradation of the dissolved substance is a first order reaction. So which means the rate of the reaction will change with time. If you have less of the reactant remained, the rate of the reaction will be less. But why here it looks like a zero order reaction, and we call it apparent zero order reaction? Because whatever amount of the reactant that disappear here will be replaced by fresh reactant from the particles. So the degradation of the reactant here is first order reaction, but because the concentration remains constant, which is the solubility of the reactant, it's been freshly replaced by the suspended particles. The reaction looks like a zero order reaction. That is why we call this apparent zero order reaction. And this is, you can look at the handout. There's some details about this concept. What about second order reactions? When we have more than one reactant, the exponent within the reaction that we talked about before will be 2. So we call it a second order reaction. These are very rare reactions to happen. Why? Because usually when we talk about order of reactions, we talk about the elementary reactions. So when we deal with elementary reactions, usually the reactants are only one reactant. We do not deal that much with the order of the overall reactions. We deal with the order of the elementary reactions, which are only one reactant or two reactant. So we do not deal with more than 2 reactants when we talk about order of reactions. This is the formula for second order reactions. And as you see here, just like first order reactions, the rate of the reaction will change with time. But here, the difference between first order reactions and second order reactions is that the half-life will increase with time. So the rate will decrease with time, just like first order reactions. But the half-life will change as well. As you know, in first order reactions, half-life was constant. But here, half-life changed as well with change in the concentration of the reactants. And this is the formula for half-life. As you can see in the formula, we have something referring to the concentration of the reactants. So that means the value for half-life actually depends on the initial concentration or the concentration of the remaining reactant. Now, we know these 3 major orders of reaction: 0, first, and second order reactions. Now, how to determine the order of the reaction? We have a few methods, like graphic method, in which we will monitor the change in the concentration of the reactant with time, and we build a diagram, just like we talked about. If the relationship with straight, that means we have a zero order reaction. If we had a curve, that means we have first order reaction or second order reaction. and then by monitoring the half-life, if the half-life did not change, that means we have first order reaction, and if the half-life was changed and the relationship between concentration and time was not a straight line and a curve, that means we have a second order reaction. We have few factors that affect rate of reactions, which we have to consider when we talk about stability of pharmaceuticals, because these all affect many steps in pharmaceutical development, storage, administration, and stuff like that. Factors are temperature, medium effect, and here there's a brief summary for the effect of these factors on the stability, catalysis effect, and some other factors. What's really important to know that usually increasing temperature increases the rate of the reactions, except for few reactions in which the reaction is exothermic. Medium like pH, like polarity, and stuff like that all affect reactions, whether it's a degradation reaction or decomposition or any other type of reaction, in which we are, by the way, here we are concerned with degradation reactions because we talk about stability. Catalysis, you know what is a catalyst? It's like a component of the reaction that is not involved with the reaction, but it affects the rate of the reaction. So it does not react by itself. It just like increases something called activation energy that we will talk about later. And we have other factors to consider. Why we talked about stability here and what's the relation between kinetics, stability, and pharmaceutical applications. Here is a small paragraph that tells us knowledge about stability is really important. Prediction of stability is really important. We have to have an idea about the order of reactions and the rate of the reaction to be able to predict stability of pharmaceutical products and to make certain predictions to know when the drug will degrade and or how much time the drug it takes for the drug to remain fit for the intended use. And here it says pharmaceutical decomposition reactions can be classified as hydrolysis, oxidation, isomerization, epimerization, and photolysis. And these reactions all are affected by the factors that we talked about before.